I have created a small replica of the model to explain what we have done and a good usage of AnyLogic in this particular context. So in our organization, and of course in every place, the spares you can easily classify as either rotables or repairables or expendables. Expendables are the ones that are one time fail, you discard the spares and you take the other ones. So that is more like a general I would say inventory management. The rotables and the repairables are the ones which are more expensive and which can be repaired. Of course, the life of the spare keeps on degenerating, which with each subsequent repair that you are doing. So our focus of this entire analysis is on the rotables and the repairable spares. More on the repairable spares, I can say. So, of course, the underlying theme behind this initiative is that either you keep a very high number of spares for any kind of an exigency or a worst case scenario, and you have a good service level, but then the inventory carrying cost is significantly high, or you optimize on reduce on that part, but that can affect your service level. So straightforward terms, we are talking about a trade-off between the the inventory and the service level. So the idea of this initiative is how much of spare you should have, how much of redundancy in the system you should have to get the target service level. So yeah. Now, what is a typical cycle that this particular example had? Is you have a spare that is on you have I would say a component that is in a working condition, then it has a breakdown. Of course, then you do a replacement because you have the redundant equipment for it. You do a repair, and then it is again available in store to do to be used for the subsequent thing. Now, one of the important things that happens is when I am anticipating how much of spares to keep, one thing is how frequently the spare is going to fail, or when it is going to fail. So a very simplistic method would be, I look at my previous history of failures and I determine, as somebody was saying, look at the mean time between failures, and as a probability distribution or a range of it I take, and take that to be the typical failure rate. If a better method would be, I take the, of course, this is something which we show in our analysis as an outcome, is that the failure was a function of course, you could look at the MTBF. It was also dependent upon the same component, which machine it is getting used to. It was more like I would say more like a stamping machine. What kind of a raw material is getting stamped into, a pressing machine? What kind of a raw material is getting used into? How many past maintenance interventions have happened in the near future? And under what operating conditions? So there was a pressure, that was employed, there was an oil temperature and other things. So all these things would give me a better prediction of the failure rate. When I say failure rate, means what is the anticipated time for the next failure? You're not able to see. What is the anticipated time for the next failure? So the intent of, or the way we went ahead doing this is, first we created a failure prediction model. So this activity was done, independently, outside of AnyLogic. Create a failure prediction model, and then, whenever we are running, so we have a failure prediction model that was built on Python and everything. Then for every run that we are doing of the simulation, we are adding the other the causal factors that are there into the model, and creating a more comprehensive integrated model, which was, I think we used a classification tree in this particular case. Then capturing the current average operating condition. So suppose if I'm running it today, that is of 19th of November at this hour. So what is the typical product that I'm making? What is the, the press that I'm putting, the oil temperature, or whatever causal factors, I would say impacting factors that are there, which I've taken in the current condition. Then do a system simulation, And because my objective, so what was my objective of this model is I wanted a targeted OEE equipment performance while minimizing my spare part inventory. And the end thing is, once I'm able to get, the idea was optimization of the spare part count. So this is something which we use the OptQuest that comes as part of AnyLogic. So in this demonstration scenario, I've taken a simple case. So suppose there are two machines which has a repairable component, and that component, the failure of it depends upon the total time that I have used, the number of interventions, the operating pressure, and there are many other factors also that are there. And there is a given work center where these things can, as I said, these are repairable. There is a given place where I can, repair these work centers that also has a finite capacity and more or less defined time. And my objective is to ensure a particular run or availability of the machine. We have used an agent-based simulation model to model the entire scenario and then capture the current, also taking the using the Python-based library to predict the next failure. And when we are continuously simulating for the next 1 month. And then we are using the OptQuest to finally optimize how many spares do we need for this particular purpose. So I'll just, 1 second. Very quickly I can run the model also.